This playlist deals with some aspects of Eurocode 2 version 2023. This video will handle clause 8, ultimate limit state, and the first in this series is talking about shear. Just bear in mind there will be 4 videos dealing with shear. So this is the first video, shear 1, and it will explain the situation where the shear stress is smaller or equal to the minimum shear stress that concrete can take up. First, we have to ask ourselves, why is it needed to have an update of the current design procedure? What was wrong with the current design procedure, or what can we make better? To explain this, I borrowed some graphs from the reference background document, which is stated here, composed by Muttoni, Ruiz, and Cavagnes. And from the different data, for instance, 669 tests, if you group them together into a graph with the x-axis, the effective depth D, and on the y-axis, the ratio of the resistant shear force from the test divided by the one predicted by the present Eurocode version 2004. So when you look at this graph, then you will see everything which is smaller than 1 is unsafe. So you see immediately there are quite unsafe results in the tests that were carried out. So unsafe design solutions in the case of large values of the effective depth D and the size effect law had to be corrected. And so when D gets bigger, then you will see there is none of those test results in this region. So this was not okay. On the other hand, when we have tensile forces, then and you look again at the stress, then the shear stress, then you will see that this is too optimistic, it's too safe, and it's clear. So too conservative for members subjected to actual tensile stresses. So that's in a quick way to explain why we need an update of the current procedure. The aggregate size, DG, which governs the aggregate interlock capacity, was neglected in the 2004 code. So the code of 2023, the shear resistance is based on the critical shear crack theory. And we will first give you an overview of the procedure. And the first step in this procedure is a detailed verification of the shear resistance may be omitted, provided that the applied shear stress is smaller than a minimum shear stress that the concrete can take. This first step is new. This is something which is not existing or not directly existing in the present Eurocode. The second step is no calculated shear reinforcement is required in regions of members where the applied shear force is smaller than the shear force that can be taken by the concrete alone. And then the third step, if this is not the case, then you should apply shear reinforcement and make sure that the applied shear stress is smaller than the resistance shear stress. First thing that we have to note is that we are talking in shear stress. We are not talking in shear force. That's also something that they put through in a consequent way. The critical shear crack theory is based on a shear crack criterion. And this criterion is derived as follows. On the x-axis, you have the strain of the reinforcement multiplied by d over dg. And on the y-axis, you have the Vc divided by Bd, which is the shear stress, divided by the square root of the compressive strength of the concrete. So the unit is square root megapascal. When you investigate a shear crack and you apply a load deformation curve, then for different load cases and deformation curve, you will end up, for instance, this is the load deformation path, and you will end up here with a failure of the structure. So now this resistance of the concrete alone to the shear force is due to dowel action, of course, of the longitudinal reinforcement, the residual tensile strength of the concrete, and then the dark blue is the aggregate interlock, and then fourth contributor is the compression zone of the concrete. You will see here where the different input data to obtain this curve. And so this is a failure criterion, and this failure criterion can be written as what is stated here, Vc over Bd, which is the shear stress, is proportional to the square root of the concrete compressive strength multiplied by a function, and this function depends on the crack width and the maximum size of the size of the aggregates. The crack width, the critical crack width, is proportional to the strain multiplied by the effective depth, the strain of the longitudinal reinforcement multiplied by the depth. All this is based on this reference background document. Fc is a concrete compressive strength, dg is the maximum size aggregate, W the critical shear crack width, and Vc is the shear strength without transfer reinforcement. Transfer reinforcement is the shear reinforcement. It can be stirrups or bend-up bars. And transfer reinforcement, you have longitudinal reinforcement and transfer reinforcement. The applied shear stress is equal to the shear force divided by BW and 0.9B, which is the well-known formula of Professor Walderhavens. What is new in the code is the next step. It is the definition of the resistance of the concrete, of the minimum resistance of the concrete, which is equal to this formula. We see that the material coefficient of concrete, gamma V, is different for shear force than for other situations. Gamma V is now 1.4 for ULS persistent and ULS temporary, and 1.15 in ULS accidental. This differs from the well-known material coefficients for concrete, which is 1.5 and 1.2. It is also strange that there is a combination of a characteristic value and a design value. So I do not understand why is it not the characteristic value of the concrete and the characteristic value of the steel, reinforcing steel, why is it a mix? You can also, for instance, take FCD instead of FCK, that will be fine too. So why is the difference there? DDG is the factor taking into account the value of the coarse aggregates. It is based on 16 millimeters plus the lower. 16 millimeters was the standard or the aggregate size where the whole system was based on. The lower, we'll come to that just now to explain the lower. 16 millimeters plus the lower must be smaller than 40 millimeters for a concrete quality smaller than 60 megapascal. When the concrete compressive strength, the characteristic value of the concrete compressive strength is bigger than 60 megapascal, then you use for DDG this formula. Now, the lower, it's something that did not exist in Eurocode 2 of 2004. The lower is the smallest value of the upper size D in an aggregate for the coarsest fraction of aggregates in the concrete. So you will see that the lower is not always known. It's not known for existing structures, or it's most of the time not known for in a design phase. So it's a little bit a problem to give a certain value to the lower. Interesting to know is that the lower has an influence on the total resistance of the resistance of the concrete against the shear. So the lower, the less resistance you will have. So we recommend to use the lower equal to 16, which gives you a safe assumption on the resistance of the concrete to shear. The Eurocode 2 of 2023 says that in case Dmax is known, which is in most cases there, you know Dmax because it's related to the environmental impact or the environmental protection. So when you know Dmax, then the lower can be replaced by Dmax. So when taking the lower equal to Dmax, it's clear for the designer what to use for the lower. But again, if there's any doubt, take the lower equal to 16 and you are on the safe side. In planar members, the design shear force per unit width is given by this formula. It's the square root of the shear stress in the x direction plus the shear stress in the y direction. This is new. This was not previously stated in Eurocode 2. This is not the same as punching shear. It's different than punching shear. I'm talking here about design shear force per unit width. The effective depth is then given by this formula, and the angle alpha V is the tangents of the angle is the proportionality between the shear stress in y direction and the shear stress in x direction. What is interesting is that the maximum width to average out the shear force in planar elements is equal to 2D. So when you are using finite element methods and you have to read out the applied shear force, then you know that you have a maximum that you can average out of a distance of 2D. The reinforcement ratio of the longitudinal reinforcement in X or Y direction can then be calculated by those formulas. The question arises here, what is the control section for planar members? The width and the height, what will it be? And then what happens with the formulas for the shear reinforcement in X direction and the shear reinforcement in Y direction. Here you make a combination of the applied shear stresses to obtain a shear stress where you are, and this shear stress will be needed to design the shear reinforcement. But in which direction is it? Is it only valid for shear reinforcement in X direction, which is equal in Y direction? It is not very clear. In regions or the regions where strength verifications may be omitted are given in this figure. This is region 1, for instance. In those regions, verification of shear strength can be omitted. This region is for a concentrated load. So when in cases of predominantly distributed loads, you can use this. And in cases of predominantly concentrated loads near the supports, you can use this. So in those regions, you can omit a detailed verification. In case of distributed loads, the design shear force may be reduced by delta VED, calculated as the sum of the distributed loads acting closer than D from the control section, but not larger than 1/4 of the total contribution of the distributed loads to the design shear force, the control section. So you subtract delta VED from the VED that originally was there at your control section. You can also translate this in a formula, but be aware this is not a formula from the code. It's just this translated. And delta VED is then the minimum of VED divided by 4 or Q times D.